Welcome everyone at our ITMP seminar. And today we are happy to have Chrysoula Markou from Mons University, and she's going to speak about the string spectrum. So please, you are welcome to start.
Nice. Thank you, and hi everyone. Many thanks to Professor Arkady Teitlin and also the organizers, Dr. Mitya Ponomarev and also Klopunov, for this opportunity. I will talk about the string spectrum today, what we know about it, what we recently discovered with Evgeny Skvortsov about it, and what remains to be explored in the future. So, right, let's start with some general considerations about string theory and what we know about all kinds of string spectra, at least the ones that we're going to consider in this talk. So first of all, in every string spectrum, there appear two string parameters: the string scale, the alpha prime denoted here, and also the string coupling. The string scale is dimensionful, the string coupling dimensionless. And we can think of string theory as an expansion using the string scale in terms of random topologies. At the same time, we can extract effective actions at low alpha prime that may be matched in the massless limit to field theories. It is important to note that expansions in alpha prime are independent or are valid at every order in the string scale, and vice versa. Expansions in the string coupling, and vice versa. Expansions in the string coupling are valid at all energy scales. And also, it's important to note that only alpha prime is a free parameter here. The string coupling instead is related to the vacuum expectation value of what we call the dilaton, a scalar field in the bulk of string theory. Now, when it comes to the spectrum, every string spectrum consists of infinitely many physical states whose mass square is inversely proportional to the string scale. And there's always an integer factor of proportionality in front that, for example, for open bosonic strings is n-1, where n enumerates the levels of the open bosonic string starting from n equals 0. Now, all of these states are physical and can be thought of as mass eigenstates of the string spectrum in the sense that their mass is on shell. And at the same time, their polarization tensors satisfy transversality and tracelessness conditions. So they can be thought of as irreducible representations of the little group that is SOD-1 and SOD-2 for massive and massless states, respectively. Now, because of these properties, it is enticing to think of all these infinitely many physical string states as one-particle states in the sense of Bargmann and Wigner. Especially for the massless case, the massless level of all these string spectra, this is actually a consideration that makes sense, and that's how we extract field theories from the low energy limit of strings. How does one now construct physical string states? How can one write such a generic physical state? There's various ways. One is the one called the light cone gauge, in which one uses the Fourier modes of the string field, the bosonic oscillators, as people call, and as I will call from now on, to construct a string state starting from the vacuum. And there is also the DDF construction, the Giudice, Di Vecchi, and Fubini, DDF as is known, where a general state can be thought of or can be constructed by means of the scattering of a certain number of vector bosons of the open string spectrum, for example, of the vacuum state of the theory, namely the tachyon in this case. So there's two of these ways, for example, which, however, are non-covariant and also lead to a superposition or even a fraction of states. And in principle, despite these 2 points, one can reach any level using either of the two constructions, so an arbitrary level n, and probe all states of that level. Now, there's an alternative way of constructing string states that is, however, covariant, and that is by means of vertex operators. This is particularly useful for scattering amplitudes because then scattering amplitudes become vacuum expectation values of vertex operators that correspond to the external states of a given string amplitude, which can be then computed using Wick's theorem. So that's why one turns to the covariant way of vertex operators. And in fact, because of the state operator correspondence, there's a one-to-one way of matching physical states, saying, starting using bosonic oscillators to vertex operators. So let's see how that works. By alpha here, the bosonic oscillators of the open bosonic string are denoted. Mu is a space-time index. And the integer here, and let's say I, essentially enumerates the Fourier modes that act on the vacuum to create the respective string state. Now, using the state operator correspondence, every such bosonic oscillator can be mapped to a derivative with respect to the worldsheet acting on the string field X. And so now the integer that enumerates the Fourier modes becomes the conformal weight of each of the derivatives acting on X in the right-hand side. It is important to remember in the following that X is not, with respect to the CFT, the conformal theory of the worldsheet, that X is not a primary field, whereas dx is and has weight 1. And every other derivative, let's say d to the n acting on X, is a descendant with weight, conformal weight n. The vacuum state is also mapped to this exponential, where P is is the momentum of the respective state or level. And it's easy to see that this is actually a momentum eigenstate. This exponential is the momentum eigenstate with respect to space-time translations. So this is a way of constructing covariant vertex operators, so to speak, at least schematically for now, using the state operator correspondence. Now, a way to visualize trajectories in the string spectrum is in terms of what people call Regge trajectories. And in that sense, there is, for example, a simple trajectory that one may construct, the so-called leading Regge trajectory, which consists of every state of every level that is the highest spin state of the respective level. So, for example, for the case of the bosonic strings, a general such vertex operator that describes the whole leading Regge trajectory it can be written as this function here. So it is this polynomial that contains only first derivatives of X. So each of these derivatives has conformal weight 1 and the momentum eigenstate here. And these they are contracted by an a priori arbitrary symmetric tensor rank S. And further, transversality and tracelessness are imposed on this tensor. So the leading Regge can be described by this vertex operator here. Sagnotti and Tarona further studied this extensively, this trajectory, and examined and derived 3- and 4-point amplitudes for the interactions of this trajectory with itself and with a vacuum. And then also, Schlotterer and Bianchi, Lopez, Richter, and Teresi studied superstrings and heterotic strings in regard especially to the leading Regge trajectory, also decay of super heavy strings. Further, and more recently, Gross, Rosenhaus, and also Firota, Bianchi, Sonnenschein, and Weissman considered what happens if one goes very, very high up the open bosonic string at a very high level n. And what they seem to find is some chaotic traits of the string spectrum, a certain chaotic trait of the string spectrum, in the sense that for a very high n, two slightly different states have very different decay amplitudes in terms of tachyons, for example. And this is actually an active area of research. Now, let's consider more general vertex operators and how one may construct them. So first of all, this is a generic form of a vertex operator. And the vertex operator is a conformal field of the CFT of the conformal theory of the worldsheet. So it has to be a primary field so as to compute invariant string scattering amplitudes. And also it has to be a space-time scalar. So all these derivatives here They have to be suitably contracted by a priori arbitrary tensors, such that the full object is a spacetime scalar. Now, such a general expression is not enough to describe physical states. One further has to impose a physicality condition. And how does one perform that? One has to construct the BRST charge on the worldsheet, which is known, and impose that this commutator acting on this general vertex operator is nothing other than a total derivative. Now, for a general vertex operator that describes a general level or a general state, if you'd like, this implies that it has to be a primary field with weight 1, and further, that the momentum eigenstates conformal weight, that is in general alpha prime p square, is to be equal to an integer minus 1, so that for the full object to have weight 1, the polynomial in front over here has to have weight equal to that integer, which is nothing other than the level. So to remember from now on, the weight of the polynomial in front of the exponential of any level, any physical level, is to be equal to the value of that level. So let's see how that works in practice for the lightest levels of the open bosonic string. For the lowest level, n equals 0, it is a trivial choice for the polynomial. So just the momentum eigenstate is sufficient to construct the level's vertex operator. There's a single state, and it's a tachyon, because m squared is negative in here. Next, for n equals 1, again, there is a very simple polynomial, only just one option. The only object in the open bosonic strings that has weight 1 is the x. And you see in front a priori an arbitrary tensor that renders the whole object a spacetime scalar, which, however, becomes constrained after checking, if you'd like, the physicality condition. In particular, the physicality condition is not trivially satisfied in this case because Wick's theorem may yield higher order poles, and in particular gives, in this particular example, a third order pole, which is cancelled only if this vector here is transverse. Next, for n equals 2, level equal 2, there's two possible cases, dx or d square x, so a descendant starts coming into the game. However, upon writing this general ansatz involving these two terms with arbitrary coefficients and checking the physicality condition, one finds that only a single state appears is physical in this at this level, and it is actually a massive spin-2 tensor of this transverse and traces. So you see that all these three levels contain only one state per level. Things, however, become more complicated as level number grows. So you see here at level 0 the tachyon we just discussed, and the massless vector that is the only massless state of the open bosonic string spectrum, the massive spin-2 that we saw here, and then suddenly more and more states per level grows along the perpendicular axis to the bottom, become added at every level. And at least the lowest levels, it is straightforward to obtain just by writing the general ansatz per level, imposing physicality, solving the constraints, and the spectrum, the decomposition into reducible representations with respect to the level group appears. Now, despite this fact having been known for decades, there is no obvious pattern that one may recognize, at least has not yet been recognized in this picture. However, we do observe a certain kind of repetition. For example, you see here in red the leading Regge trajectory, and you see over here at level 4 a massive spin 2, and followed by a massive spin 3, and so on, much like the massive part of the leading Regge. So you see, if you'd like, a clone of the leading Regge starting at a higher level, n equals 4. But other than this repetitive pattern, there is no organizing principle that is immediately available so as to consider the whole spectrum. So what does a state, a generic state, look like? First of all, any state is associated with a physical polarization tensor that we may denote by epsilon, where we group with space-time indices mu different groups of symmetric indices. And visually, such a state may be represented by a Young diagram of this kind. So you see here n rows, and the number inside every row represents the number of boxes per row. And we may think of rows as symmetrizing space-time indices, whereas columns as anti-symmetrizing, as in the first approximation, if you'd like. So any state of the string spectrum can be represented by such a Young diagram, whose particular symmetry properties should represent the symmetry properties of its polarization tensor and satisfy as determined by physicality. Now, conversely, a given Young shape it is possible to embed a given Young shape in infinitely many different ways into the string spectrum. And let's see how that works. It is straightforward to convince oneself that this shape appears at the lowest possible level that is given by the weighted sum of the number of boxes per row that the diagram has. So any diagram can appear at this lowest level inside the string spectrum, the open bosonic string spectrum. Such an example is the leading Regge trajectory. So if we go by here, the spin 2 appears at level 2, spin 3 at level 3, and so on and so forth. Now, it is possible to imagine, however, because of the repetition that we just highlighted, that any such diagram may further appear infinitely many times at higher levels. And let's denote the difference in units of those higher levels with respect to the lowest possible level by this integer w here that we may call depth in the following. So for example, going back to the spectrum here, this trajectory highlighted in gray that starts at level 4, so the spin 2 here starts at level 4, can be thought of as being at depth equal to 2 with respect to the leading Regge trajectory. So you see here, spin 2 of leading Regge starts at level 2, but spin 2 of this subleading trajectory starts at level 4. Because this integer here, in fact, parameterizes the whole trajectory, we may think of, as Zhenya pointed out in this joint work, as a new possibility. We may think of this depth as a new possibility as to organize the spectrum. So until now, we had level so as soon as the mass level and the spin or the Young shape and also the multiplicity of the state was determined, the state was fully determined. And now let's think of the depth instead of the level as sufficient, along with multiplicity and the Young shape, so as to determine fully the physical states. Moreover, let's call a trajectory a certain Young shape that has a given number of rows. So for example, the leading Regge trajectory consists of all diagrams that have a single row, such that as level number increases, boxes get added to this row. And so it is the set of states of spin S at level S and depth 0, because recall, it's the lowest possible level for every state. And with respect to the clone of this leading Regge highlighted in gray previously that I was mentioning, again, it is a trajectory of one-row diagrams to which boxes get consecutively added to this row for the level to increase. And now this clone consists of all states of spin s minus 2, which however find themselves at level 2 units up, namely at level s, with a depth being equal to 2. Alternatively, we may think of this clone as a set of states of spin s that find themselves at level ns plus 2. So there is a difference of 2 units between these two example trajectories, leading Regge and its first clone. However, every trajectory appears in infinitely many clones, and there's infinitely many trajectories as well. This picture that we have here in terms of depth may highlight this. For example, here you see some of the trajectories that appear at weight 0. Again, you may think of all these different Young shapes as trajectories, with spin being corresponding to a third axis, if you want, that goes inside the screen. And all these trajectories are the first instances of these of the respective Young shape inside the spectrum. As depth increases in this axis as we go to the bottom, then we have similar Young shapes, the same Young shapes get repeated, but at higher levels. And so the way to write the respective polynomials rises in complexity as well, becomes even more complex with respect to weight 0. And in here, inside every Young diagram, we have if there's a way to parameterize the number of boxes with respect to the weight. Now, based on this picture, with Xenia, we started thinking about more general vertex operators that do not necessarily correspond to a certain level or even a certain state. So to distinguish the situation, let's denote these by math BB V, so not a certain level, and let's consider a general polynomial in here times the momentum eigenstate. And for simplicity, because we can have any descendant in here, not tied to a particular level, let's use this kind of notation. So this index k on x tells us how many units of conformal weight of descendants we use inside the polynomial. And also recall that this p now, it is a parameter, it is the momentum, but however, it should land to the particular level once physicality is imposed where the respective polynomial makes sense. Right. So now let's consider this general vertex operator with a general polynomial and impose physicality on it. It is straightforward to compute using Weck's theorem, this OPE. And what we find is two things. First, the on-cell condition that we also know from the light conform relation, if you want, or the previous language of the simple vertex operators. So in here, we have nothing other than the number operator acting on our general function f. This equation lands our momentum to the respective physical level where f makes sense. And we also get n differential constraints, so infinitely many differential constraints that I give here. And out of these, the leading Regge trajectory is now the special case where the function f depends only on the primary fields of weight 1, the x's, or if you want, x with index 1. Now, let's observe this equation a bit more, this differential equation. We have derivatives with respect to the descendants, and they seem to appear with these particular combinations. So for example, here we have two derivatives with respect to descendants that vary by a unit of n. Based on this observation, it makes sense to define first these kinds of structures. So first, an operator t with one index up one index down. Recall that k runs from 1 to infinity because we can have infinitely many descendants in principle appearing in the polynomial. Or let's say up to a certain number k, which may, however, run arbitrarily high, better put. And this operator is just this Minkowski product of x indexed by k times the derivative with respect to a different descendant of weight L. Similarly, we can define this operator with two indices down and this with two indices up. And recall that this must have weight k minus L, and this operator, for example, k plus L. What is interesting further to note is that now Minkowski indices have disappeared because only these dots are here, Minkowski spacetime, products. So everything is Lorentz covariant, and we only see the k indices. Now, one may further define these kinds of operators where p appears as the zeroth, if you want, for value 0 of the index k, with respect to this operator with one index up and one index down. And then it is straightforward to write Young symmetry and traceless and transversality conditions for general functions denoted by a small f here. So for example, this is Young symmetry now for a general small f. This is transversality, and this is tracelessness. Now, what Genia realized in this context is that the set of these three operators highlighted in turquoise, they form an SP algebra, the SP2 bullet, which is actually Howe dual in the sense that it commutes with the Lorentz group in spacetime. Recall, the T operators know nothing about Minkowski. They have indices k and L, which may run up to an arbitrarily high value of k, whereas Minkowski is a smaller, the spacetime and the Virasoro are smaller groups for the string. Moreover, if one adds to these operators T with one upper index 0 to account for the momentum, and so be able to impose transversality so as to get irreducible representations of Poincaré in spacetime, one forms with these four kinds of operators a subalgebra of SP2 bullet plus 1 now, which now commutes with Poincaré in spacetime and what has come to be known as Howe duals in the sense that they commute. Now, because of this observation, it makes sense to consider this symmetry, this SP symmetry, that is bigger than the Virasoro, in order to start constructing trajectories. And in fact, there is a simplification that one may find, for example, in Magnes and Vosmediano, as pointed out to us by Professor Zeitlin, in the sense that the transverse subspace is sufficient to enumerate and construct physical states. And for our purposes, this effectively means that we make no terms linear in P that one may also prove to be BRST exact. So they do not contribute to scattering amplitudes. The implication of all this discussion then becomes that we may construct physical string states as the lowest weights of SP2 bullet. So we may use the creation operators of this bigger algebra compared to the SO that we have in spacetime, so as to write states and hopefully also trajectories, which will be the case as we will see. Now, in the SP language, our constraints, also using the transfer subspace simplification, take this much simpler form as you see there. Moreover, as was previously realized in the light cone gauge, only three conditions are sufficient. So L0, the on-shell condition, if you recall, and also only two more, L1 and L2. And this is because of the Virasoro algebra. This was previously shown to be the case for any state or any level. Now we show that for any kind of function, even more general, that may be probing several states or whole trajectories, these two conditions remain sufficient. So the differential operators we have here also satisfy the Virasoro algebra. And no matter how complicated the state or level of trajectory you want to prove is, only these three conditions are sufficient to solve to fully determine the physical trajectory, state, or level.
Could you say more explicitly what happens in light cone gauge? So all this structure sort of disappears, or what happens in light if you use light cone gauge?
Yes. You mean here the conditions? Yes. So
yes.
There, if one writes down L0, L1, and L2, because of how the algebra looks like with the Virasoro, every L3, L4 can be reproduced by L1 and L2. So if L1 and L2 are satisfied and solved, then every other is a consequence and does not further constrain our physical ansatz in any language, light cone, vertex operator, and so on. Okay?
Okay, thank you.
Thank you. Okay. So based on these considerations, remember the depth, which is the difference of the level that a certain Young shape can appear at with respect to the lowest possible level that the same Young shape can appear at. And also the consideration of Howe duality, which allows us to use the creation operators of this larger symmetry, the SP, so as to construct states. We may distinguish two kinds of embeddings of physical trajectories inside the spectrum. So with Genia, we called as principal all states, all trajectories that appear at weight depth equals 0. Sorry, not weight, depth. For example, the leading Regge is part of the principal embedding, and a general such trajectory looks like this. So a general polarization tensor, again, come with separate groups of symmetric indices, and then you have all kinds of descendants you want symmetrized. So this principal embedding consists of all first instances of all trajectories of the string. And if you want, the value of k is of the number of rows that you have. For example, leading Regge, as we said, it has one row, and then as k increases, so number of rows increases, we get to new trajectories, and so on. This already makes clear that complexity of a state and spin, if you want, does not necessarily increase with upon increasing rows. So things are more complicated than that. Now, moving to non-principal embeddings, as we call them with Xenia, for non-vanishing depths, the idea is basically in this equation here. So take any trajectory of weight 0. It can be any of those of the principal embedding, and they act on it with this operator here that may be constructed using all possible creation operators of the SP2 bullet here in the simplified transverse ansatz. And these are just t with two indices and t with one index up, one down. Now, this object we call trajectory shift because it has weight equal to the depth that we want to reach. This resulting state to the left finds itself at level equal to the level of the original state trajectory we acted on plus the depth. And let's see how this works in an example. Here, the red is the set of leading Regge states, so the leading Regge trajectory. And let's parameterize those states as having spin S-2 at level S-2, just for convenience. So red is leading Regge with spin s-2 at level s-2. Then say that we want to reach depth 2 in the left-hand side, so highlighted by gray. In other words, we don't want to change the spin. Spin remains s-2, but now level is equal to 2 in the left-hand side. I repeat, spin s-2, spin s-2, both left-hand side and right-hand side, but level here is s because this trajectory shifting operator in turquoise adds 2 units to the level s-2 of the leading Regge trajectory. And inside this trajectory shifting operator, we have all possible terms that we can write using the creation operators of SP that have weight 2. For example, here we call 2 indices up mean that the weight of this operator is equal to the sum of the values of the indices, so this is weight 2. This is the difference of weights, so 3 minus 1 gives 2, fine again, and this 2 minus 1, 2 times, so again we have weight 2. And these 3 terms are thus the only possible terms that we can write of weight 2, and we weigh them by a priori arbitrary coefficients on which we will determine by imposing physicality. So by imposing the PRST condition, we can fully determine the full trajectory that is the clone of the leading Regge of spin s-2. And in fact, we have the full solution with Genia, and it only depends on one parameter in the end. So there's only one free parameter, along with a number of dimensions and the spin, so that it can be restricted to any spin, namely any state you want. Let's see, for example, what happens if we restrict to spin 2. This appears at level 2 units up, so 2 plus 2 equals 4. And by restricting a formula for this spin, we find this relation here. This is, in fact, as should be clear, the trajectory shifted massive spin 2 from level equal to 2 at depth equals 0, where if you remember, it was just this polynomial dx. Let's go back to the spectrum to see. So we had this, and now we have constructed this massive spin 2. It's first clone, if you'd like. But it's actually more powerful what we have done than just getting from this massive spin 2, the lightest massive spin 2 of the open bosonic string, to its first clone. We have actually constructed the full trajectory starting from the leading Regge. If we compare with the old formulations, for example, the standard vertex formulation, to reach this state, we would have to write all possible terms that describe this level, solve physicality, and then perhaps it would be slightly more hard than the n equal 2, but still doable. But then we would only have this massive spin 2 vertex operator, and we would not be able to guess using this form the rest of the vertex operators of the same trajectory. So yes, please.
Can you explain why, like on the picture, you don't have the counterparts of a scalar and of a vector in the third trajectory? It's from spin 2, right?
Yes. So this is yes. I would say this is a peculiarity of the way the string spectrum is. So this is the vector that is massless, and the tachyon that is massive but still a tachyon. So these two states are particular, and we never see them again in the spectrum. This scalar, for example, it's not a tachyon. It's a physical. Well, all are physical, but still, it's a stable. It still corresponds to a stable vacuum of the theory. All other vectors also that we see, they're massive. So we're not even talking about the same little group when we compare with this. And moreover, the tachyon will disappear when we go to the superstring, so we don't even have to think about tachyonic instabilities.
But like in principle, if you try to apply your raising operators to these two states, do you get 0 or something else? Or it makes no sense?
You mean to take, for example, the exponential and apply the...
You have that combination of SP2 generators that
Yes.
moves you from the first trajectory to the third one, right?
Yes. So
Right.
yes. So let me put it like that. The whole these two states we know how to describe well. We don't need them to start describing the other scalars and vectors that are massive and appear in the spectrum. Those, they're part of new trajectories that are also part of the principal embedding. So again, the principal embedding, if you'd like, is the hardest to construct, and you have to start from scratch.
Mm-hmm.
You see what I'm saying? So again, the trajectory that starts with a scalar is a new trajectory at depth equals to 0.
Mm-hmm. Well, another thing related to this, you said that the leading trajectory apparently is annihilated by some annihilation operators from SP2. Is it correct? You said that you act by raising operators if you want to get others.
Okay, so any state, if you want, we can construct by looking at the lowest weight states of the SP. And how can we construct those? Using the creation operators of the SP. This is not particular to a certain trajectory. The whole spectrum, this is what essentially we're doing here. The whole spectrum we're trying to construct using those creation operators of the SP.
Mm-hmm.
Okay.
Yeah. Okay. Thank you.
Thank you.
Could you also give some idea where are you moving? What you want to achieve? Or...
Yes. So ideally, with Genia, we would like to have to probe the full spectrum to find a new organizing principle so that any state of the spectrum is accessible. Right now, we have the machinery to go from depth equal to 0 to any other depth. For high depths, it may start to become cumbersome as well, as we have the same with the problem as when the level, if you want, increases. But still, with our machinery, we can probe and construct whole new trajectories, and we actually have more examples in the paper. Now, ideally, we would want to be able to do this for the full spectrum and not just go depth by depth, starting from depth 0. So these are some of the questions that we're thinking about now. And to highlight an example about how powerful this machinery can become, I was explaining this difference here. And let's talk, for example, about the interactions of the subleading, or if you want, deeper trajectories of the spectrum. We have some formulas for endpoint amplitudes, which are immediately accessible using our machinery. And for example, let's look at interactions, or if you want, scattering of tachyons of a certain spin S. If the spin S belongs to the leading Regge, then we have the amplitude in red, which weighted by this factor that depends on the spin and the number of space-time dimensions, gives actually the same amplitude, but for the spin S now belonging to the example at depth equals 2 that I was just explaining. So you see now whole classes of amplitudes become accessible that we didn't have, the literature did not have access to beforehand. Whether this can be pushed even further to treat the whole spectrum, this is an open question that we would, that certainly is among the ones we're thinking about at the moment. Is that okay? Is that answering your?
Yeah, thank you.
Thank you.
But by the way, can you briefly explain what's the difficulty with defining the spectrum? So is it, does it come from imposing these physical conditions? Because other than that, it seems to just like take tensor products of boxes of vectors.
Yes. So
like at each level, you have like this many derivatives or
yes. Yes, but the problem is that to write the general ansatz, it is possible at any level, but then you have to solve the BRST conditions, which become increasingly hard as level increases. Now, with our method, with Genia, even if difficulty becomes larger, whole trajectories we're able to construct. Moreover, you saw the ansatz is just 3 terms in the transfer space, and the conditions are much easier to solve than, say, we go to n equals 10 and solve BRST, because we have general formulas for general f and general spin that you can then restrict to the values of the spin and level you want. So it's much more powerful than just going to level 10 and solving BRST.
And why are there only 3 terms? So there was some like extra indices. I didn't understand where they come from, like 2, 1, 1, 3, 2, or something like that.
Yes. So here, this particular example.
Yes.
So here there are just 3 terms because we are in the transverse simplification, so only transverse subspace, and also we want only probe a single trajectory that looks exactly like the leading Regge and finds itself at depth equal to 2. There are many more that may even look the same. So there are infinitely many more clones that we're not probing using this ansatz. But every ansatz to reach a particular depth is finite.
Okay, I see. Yeah, thank you.
Okay, thank you. All right. So yeah, illustrating after having illustrated this, the power of this machinery in terms of probing Hall trajectories and also their interactions in terms of string scattering amplitudes, let's turn to some different examples that in the recent past that I considered with collaborators from Munich, and in particular examples of subleading states of the superstring now, so that no tachyon considerations have to be put into place, and how the interactions of those subleading states look like. So, for example, let's look at the lightest massive spin 2 multiplet, supermultiplet, I mean, that appears in the open superstring spectrum. For example, for n equals 1, it has this form. For n equals 2, vectors and scalars come into play, so slightly larger supermultiplet. Now, this spin 1 here of the brain, what does its vertex operator look like? It takes this form, so ignoring for the string coupling and the brain gauge group generator, also the ghost considerations that I can explain if asked. It contains the momentum eigenstate, and now the fermionic worldsheet coordinate psi mu, where mu is again a spacetime index. Alpha mu is again a priori a generic vector that renders this whole object a scalar. But there appears also an internal Kac-Moody current, because we're considering compactifications to 4 dimensions, so as to see how subleading states can be compared to interactions of real fields if in 4 dimensions, if this comparison can make sense. Now, this J current here that appears, it appears because of the compactification to 4 dimensions from the 10 of the critical superstring. And for the case of n equals 1 supersymmetry preserved after the compactification, it is a U1 current, so it just obeys a U1 algebra. And you see then transversality that has to be imposed on this a priori arbitrary vector for the whole object to be physical. Now, this vector was already available in the literature here, but the question I wanted to answer together with the collaborators from Munich is whether we can use it to construct massive spin 2 subleading states in the closed string spectrum that we expected a priori to behave in ways similar to that of the graviton, because if you ignore this J current here, what you see is the vertex operator of the massless vector of the brain. So this J here, in some sense, is there to lift the level from 0 to the first level up the open superstring spectrum. So the structure of this massive vector is very much like the one of the massless vector, which prompted us to consider these tensor products of such vectors that lead to massive spin 2 states in the bulk in the closed string spectrum. So here again, you see that ignoring the Kac-Moody part of this vertex operator, the structure of the vertex operator of massive spin 2s of this particular kind that have been constructed as products of Kac-Moody vectors mimics very much the structure of the graviton of the bulk. However, there's more in the same supermultiplets in the bulk, there's more and also higher spin states available, in the sense that any of these two states can be the massive spin 2 of the brane and the massive spin 1 state of the brane can be tensored with themselves and with each other, so as to create closed string states, massive closed string states in the bulk. And there's higher spins that are the high spin components of this multiplet that includes this massive spin 2. However, these are still subleading, so in some sense, they are the first subleading states in convectifications to 4D probes with regard to the closed string spectrum. Now, it is interesting to see how these states interact and compare their interactions with those of the graviton. And here, you may see the 3-point amplitudes of 3 gravitons, 3 graviton and 1 such massive spin 2, as the subleading I showed in the previous slide, 2 massive spin 2s and 1 graviton, and 3 massive spin 2s. And what you see here is, in all of these cases, the external polarization tensors, the Koba-Nielsen factor, whose value changes depending on the external, the values of the external momenta, so on the on-shell conditions. And then you see 2 structures here with Minkowski indices, space-time Minkowski indices, that do not change. You see here the value of the B, and the B tilde has the exact same value, but corresponds to the left and to the right sector of the closed bosonic string. So what is interesting to note is that this B factor is the same everywhere. The way momenta enter, I mean, the external momenta enter, is the same everywhere and is not dependent on whether the external states are massless or massive. And then, depending on whether the states are massless or massive, the J currents start playing a role. So, for example, if you have 3 gravitons, there's no J, of course, so no J factors here. However, for 3 massive spin 2s, there's 2 vevs involving J's, one for the left and one for the right moving sector. And recall that for n equals 1 convectifications, we have U1, so these 2 vevs become trivial. And so the 3 massive spin 2 amplitude is equal to 0 for n equals 1 convectifications. However, it becomes non-trivial as soon as you get n equals 2 or n equals 4, because then there's a non-abelian Kac-Moody associated with a convectification, and so these vevs become non-trivial. In all cases, it's also worth noting that vevs of single objects are equal to 0, and so the decay of 1 massive spin 2 to gravitons is equal to 0. Summarizing this property, for any number of supersymmetry involved, there is no decay, at least at 3 points, of a massive spin 2 into gravitons. And here the index of supersymmetry is referring to the closed string spectrum. So n is equal to 1, 2, and 4 on the brane. And so upon tensoring the vectors to construct the massive spin 2 states that I showed to you, you get n equals 2, 4, and 8 in the bulk, respectively. Now, as far as the amplitude of 2 massive spin 2s and 1 graviton is concerned, it looks the same in all cases, regardless of the amount of supersymmetry preserved. But of course, the massive polarizations, they have to carry internal Kac-Moody indices, depending on how much supersymmetry is preserved. And as I pointed out, only for non-abelian Kac-Moody currents, so for supersymmetry higher, preserved in the bulk higher than 2, is the 3 massive spin 2 amplitude non-trivial, and it takes exactly the same form for n equals 4 and 8 in the bulk. Now I have put a tilde here so as to restrict only to the singlet component of the massive spin 2, singlet with respect to the Kac-Moody, the internal Kac-Moody, I mean. So as soon as you restrict yourself to that singlet component, the amplitude is exactly the same and no Kac-Moody indices appear. And interestingly, this amplitude is exactly the same as the universal 3 graviton amplitude. So massive spin 2 and the graviton, at least the massive spin 2 that we constructed, that is subleading and depends on this Kac-Moody current, interacts exactly the same with itself as the graviton does with itself, at least at 3 points. Now, because these 3-point amplitudes happen to be finite in the string scale, a question that may raise itself is whether we can compare with field theories that involve massive spin 2s. Even though we do not expect field theories with massive spin 2s to arise from string theory, in the sense that those are associated with a parametric scale separation between the Planck mass and the mass of the spin 2, whereas in string theory you only have a single scale, the string scale, that determines the mass and the Planck scale. The point of this comparison is solely the fact that the amplitudes are finite. The 3-point amplitudes that I showed to you that we have computed are finite in the string scale. And just to recall, there exist ghost-free theories of massive spin 2 fields with such scale separation as the one that I mentioned, and which evade decades of arguments against ghost freedom of massive spin 2 propagation. Those are the Teram-Kabadadze and Tolle theory of massive gravity with a single massive spin 2 field, but also by gravity theories, for example, the one by Hassan and Rosen that involves the propagation of a massless and a massive spin 2 field around maximally symmetric backgrounds. And in fact, upon expanding those, the gravity action, for example, around Minkowski, one gets a set of 3-point vertices with specific coefficients that can be traced back to the structure of the biometric interactions. And upon comparing with effective actions derived by our own amplitudes, we have found that there can be a match between the effective interactions we derived and the bigravity 3-point vertices, only for the case that the massive spin 2 from strings is the closed subleading massive spin 2 we constructed using the Kac-Moody currents. Instead, if it's a brane state, a massive spin 2 that belongs to the brane, then its interactions cannot be tuned, even though they're again finite in the string scale. It's the coefficient, the respective coefficients cannot be tuned to match those of bigravity. And so, in some sense, the net result of this computation is that among the lowest lying states of the superstring, there is a massive spin 2 on the brane, and there's many massive spin 2s in the bulk. Among the ones that are the lightest in the bulk, there exist certain ones whose 3-point self-interactions and their interactions with the graviton can match those that appear in a field theory like bigravity. However, we all already expect that beyond the 3-point, string theory will give different vertices, more and more vertices, and also in the identification of the massive spin 2 will start losing its meaning, as there's infinitely many copies of massive spin 2 in the string spectrum. So the similarity between the subleading states we constructed and the interactions of the massive spin 2 in bigravity, for example, it could be an artifact of the fact that 3-point interactions are simple enough and package very basic properties of such massive spin 2 irreducible representations. Beyond, we expect things to start diverging. Now, when it comes to the open bosonic string, with Xenia, we have used a symmetry bigger than the Virasoro to organize the spectrum and start probing entire trajectories deeper than the leading Regge or than the lightest possible levels. What should be highlighted is that for a given Young shape as so a given set of a given number of rows, or if you want a given trajectory, as boxes get added, complexity increases, but the number of rows remains the same, so spin doesn't change. And the bigger question that would be amazing to have an answer to would be whether it is possible to treat the entire spectrum, as we discussed before. And in particular, whether we can have a method of finding where, at what level new trajectories start and with what multiplicity. Moreover, another open question is related to black holes, in the sense that a recent work by Piccini and Cangemi showed that the leading Regge trajectory yields interactions that cannot be matched to black hole, to Kerr black hole amplitudes. And so the question remains as to whether Kerr amplitudes can be reproduced in some other way by string theory, for example, by using other trajectories, or for example, using our new machinery with ESP creation operators. And finally, there's other open questions that remain. For example, whether chaotic traits can be probed using this new machinery, and what happens with the tensionless limit of string theory that trivializes the spectrum and also makes a higher spin symmetry manifest. So this brings me to the end. Thank you very much.
Thank you. Are there any questions?
Hi, it's Maxim. Maybe I have a very technical question, but I vaguely remember something about this representation theory story. So if things are very simple, if your number of generators of this SP2M, this M is roughly speaking, it shouldn't be too high in a given dimension, otherwise you get certain multiplicities, and the representation theory becomes subtle. Do you see these difficulties? I know this from mixed symmetry fields, not from string theory, but I vaguely remember that if you consider in low, like in dimension, I don't know, 10 or 26, which one do you have? If you consider too many oscillators at the same time, which means Young tableau of sufficiently high height, sufficient big height, then things become tricky. You can get additional multiplicities, some other stuff, and we know that in this case, certain diagrams become identical. Don't you see difficulties?
It's a very good question. So what I can say is that the particular examples that we have, they always refer to a lower number, so up to 3 or 4 derivatives, so descendants, and weight of descendants, I mean. So K not very high, as you point out. And so the resulting multiplicities are never bigger than 3 or 4, if I remember correctly. So I expect the problem that you're mentioning to appear, but we have not yet been that deep into the spectrum so as to have to deal with that high multiplicity where such problems may emerge. It is an area of active research. I would add.
Yeah, because it was very technical, but I just wanted to attract your attention that there are some subtleties if you have too many oscillators.
Yes, it's a very good point. So deeper in the spectrum, we expect things to become more complicated, which is why we're still thinking about these questions. But yeah, we didn't have these problems did not emerge for the low K and low values of depth that we treated.
Thanks.
Other questions? Well, I have a question. So, do I understand correctly that you roughly have like two independent parts of the talk, or probably this like J Kac-Moody current, which you add is somehow related to these SP2 generators that shift trajectories?
Okay, so ideally, we would want to go further with this machinery to treat superstrings and so on. And as you point out, the J then would correspond to new generators. So we have to think as to what the group, the bigger symmetry in that case would be. So in some sense, I am mentioning the part with the J because it's part of where we would like to go in the future. But of course, there's several steps involved because first you would have to treat superstrings. So what we did is critical dimension bosonic strings. Then you would have to go to superstrings in the critical dimension, and then go to compactification to see how Howe duality would transform itself, like what manifestation it would take, and how the J's would find themselves inside new operators that we have a different dual. So that's the direction that we would hope to go in the future.
So those J's, they have nothing to do with these F's, despite they both change mass and don't change spin.
I would say that they do not obviously have right now, but it is something that we would like to answer in the future. So the J's, where do they come from? If you have an n=1 compactification, you start with the coordinates, the superpartners that you have in the critical dimension, the dx and the psi, and you take some components of them to be internal, so like in the 6 dimensions. And those internal components then start forming currents like the Kac-Moody I showed, such that the superalgebra closes to the amount of supersymmetry you want after the compactification. So the J is not completely independent compared to the X's that we used to form the T's, the operator T's that generate the SP algebra. But exactly how they form a new algebra and what kind and what its dual would be, it's something that we would like to reply to in the future.
Mm-hmm. Okay, I see. Any other questions? Maybe you can also explain what was that Kerr amplitude?
Yeah, so people have been thinking about taking infinite spin limits from elementary quantum amplitudes in field theory, and now this idea was pushed forward even to the leading Regge trajectory amplitudes by Evgeny and Regge. And there they couldn't find a match with Kerr. So why do I say Kerr? Because they're rotating, so you can think of them as spinning, and in the leading Regge you have arbitrarily high spin. And so now with the new machinery that takes us with Genia even deeper into the spectrum, it would be an interesting question to try to see whether there's a different trajectory or even set of trajectories that could yield or reproduce 3-point Kerr amplitudes of field theory, for example.
So do I understand correctly that this Kerr amplitude is, let's say, a scattering of a scalar field against like a classical gravitational Kerr potential, and you're trying to mimic it with some like scattering against some massive higher spin particle or something like that?
Yes, that is one way of putting it. Yes.
And you're from that you're sort of like trying to fit the family like of these particles, masses, and spins, so that one thing produces the other.
Ideally, yes, but it's not something that I'm actively working on at the moment. It's one of the questions that I have in the back of my mind, like whether these elementary, if you want, these quantum properties these general relativity properties can emerge from a framework like string theory, and in what sense. So actually, the fact that the leading Regge has no such features, you can even see as discouraging, as having string theory reproduce these results. But now, because whole subleading trajectories are available, this gives us more hope, because if you ask me personally, I would think that black hole interactions is something that the full string theory should know about, and not a truncation of its spectrum in any way. But this is super tentative what I'm saying, so it remains to be seen.
Thank you. So the final call for questions. Okay, seems that we don't have any further questions. So thank you very much for a nice talk.
Thank you, Mitya, and everyone. Yes.
And thank you everyone for coming, and see you next time.